Swayam Prabha. Digital India. Educated India.
Keep you alert. We will not talk about absorption, we will talk about densities and velocities. I hope you have not forgotten anything about the densities we talked about. So I do not want to repeat everything from the morning. So, but one thing I was really very interested in, and perhaps that's something that is common, which you can think of, is if you're trying to model these absorption sites, then you have to have a mixing model, right? You have different types of energies, you have different types of interactions. So if you want to have the total amount of absorption and energy, you need some sort of a mixing model. So the closest thing I was thinking was, there is a cable that was hanging there and I know I will trip on it. So, but I was trying to figure out, so where do we find common ground? What have you just heard? And now what will you hear? And the best thing I could come up with was mixing models. You have disparate pieces of information. You have absorption sites that have different energies, and if you have multi-species, then you have different energies, right? If you want to have a complete model for your system, you need some sort of a mixing law. And we have exactly the same problem. We have velocities here. This is my fluid velocity for brine and for carbon dioxide. And then we have the matrix. So we need some sort of a mixing law. How do we mix these two? Now, one of the things which is really interesting, and this is something people do with we didn't put that one in. Okay. Don't worry, we'll see that tomorrow then. So we'll look at the consequences of this sort of a difference in this case velocity, the acoustic velocities, how do they match in the models, and we'll look at the consequence if there is a density change in the reservoir simulation models. If we're looking at distributions, this is electrical conductivity, this is another term, another property that we use. We are investigating the differences in conductivity of the mineral constituents and the pore fluids. In the simple case, we always think of rocks being insulators and the fluids being conductors. If we have hydrocarbons or if we have fresh water, then they will become insulators. So we can have insulators in fluids. We can also have conductors in rocks, which would be clay minerals, clay-bound water, pyrite and graphite and so on. So when we investigate conductivity, electrical conductivity, we are really looking for pathways of the electrical current to go through and come out, measure on this side, measure on that side, right? So that's really what we try to do. The nice thing there is that there is a direct relationship. This is old experimental data that was conducted in the industry, in the oil industry, and this is a series of sandstones with varying porosities. If you fill them with the same fluid, pore fluid, with the same resistivity pore fluid, that occupies a very nice linear relation. And the slope of that relationship is called the formation factor. It is describing the pore pathway, the conductive pathway through the rocks. So, if you think of this as your formation, these are the rock grains, this is the fluid. If you remove all of the insulators, this is what you are left with, and this is defining what your conductive electrical pathways are. If this is more complex, you will have a lower overall conductivity. That's here conductivity of the rock, conductivity of the brine. This is the porosity, how much pore space there is, and this defines this sort of geometry. If we add in another fluid, then we start changing that pore pathway. And so, in this case, we have a resistor, an oil that we've added to the system. And now what we're looking at is not just the porosity, not just the rock porosity pathway, but also the pathway for conductive fluids to be present. And so, if you take out again all the insulators, this is the total rock, you take out the insulators, that was the rock grains from before, and you take out the insulating pore fluids, this is what you are left with as your conductive pathway. And then we can write another equation out here. This is the same as before, and we get one more term that tells us how much fluid there is, the porosity. If saturation is 1, this term falls away. All of the pore space is filled with conducting pore fluid. If we have some other pore fluid, now we need to take care of the saturation. So, this one tells us how much of the conducting pore fluid there is, and the exponent now tells us how these two phases mix. And so, we have a pore pathway and then a conductive fluid pathway. So, we play these sort of models. This is again an empirical model. This is based entirely on empirical data, but it works very well. The fudge factors that we have are these two parameters here. This equation assumes that all of the rocks are non-conductive. If there are some rocks that are conductive, we get another term out here. But fine, that's one thing. Now, in all of this, we look also at deformation. So, if this is a rock, this is a typical calcite here, a carbonate here, the purple here marks calcite, the green here marks clay minerals. We normally think of calcite being very less compressible, very stiff, and clay minerals being more compressive. So, if we were to subject this thing, and these are this is SEM picture. Out here we have 1.25 micrometers for that's a translation. This should be micrometers, not millimeters. Wouldn't make sense to have it 10 millimeter grains, but so this is 1.25 micrometers. That's the scale here. This is a X-ray image of the whole core. So, this is about 2 centimeters. And so, when we are looking at this type of rock, we want to know what the compressibility is. If we apply stresses to this rock, we have two different orientations of the stresses. How will this rock deform? And we can think of weaker materials out here that are more or less aligned, and so there will be a zone of higher compression in this direction and less compression along that direction. So, it is anisotropic for one. That means the as a function of stress, even if the stress is the same in these two directions, if the stress is the same, I will have higher compression here, less compression here. So, when we look at mixing models, we take these extreme cases. We want to look at stress because if we are going into saline aquifers, we will make use of these stress concepts. We will look at the compressibility of the fluid and the compressive strength of the rock to see how much can we put in and what is the capacity of the formation. So, when we examine stress effects in rocks, we say that on an average, minerals are less compliant than pores. We cannot, if the minerals would be your quartz, your calcite, if you try and compress that, it is not as easy. If you put pores inside it, if you put holes inside that rock, then it starts to compress more. Depending on what the material is filled with, whether it is water or gas, it will be more or less compliant. So, we then define materials by their compliance. Compliance is the inverse of stiffness. So, we have soft, compliant pores and cements that deform more with pressure. When we put stress on them, they deform more. We have stiff pores and hard cements that will not deform as much. And so, when we are looking at storage capacity, we then need a term for compressibility. How much is this rock going to compress? The part that we then examine is what properties does the stress influence. So, we have pressure effects where velocities increase with pressure. If we have cracks and compliant pores, they will close. We might get some mineral compaction. These mineral compactions will be primarily in clay minerals. If we have fluid effects, if we have fluids present, we are changing out the fluids, we are going from brine to carbon dioxide, then the compressional velocities will be sensitive to not only the type of fluid, but also the fluid saturation. Your shear velocity will not be affected by it except for a density effect. If we have a very stiff rock, then the fluid effects are not going to be that easy to discern. If we change mineralogy and we change the lithology, the velocities will change. So, depending on what type of material we have, we will have a difference in velocity. And finally, if we have layers, if we have any alignments, we will have a directional dependence of velocity. Now, the reason I am pointing this out is because most of our information comes from, most of our spatial information comes from seismic data. When we are monitoring how much carbon dioxide we have put in, where does the carbon dioxide go, we are using seismic. And so, we want to know all the influences on seismic data. We are only interested in this part. We are interested in fluid type and fluid saturation, carbon dioxide, saturation of carbon dioxide. This is really what we want to map. Along the way, we will be changing pressure that will affect our measurement. We will change perhaps the lithology, the mineralogy because of reactions. It will affect velocities, and we might be in an anisotropic environment, or we might be in a heterogeneous environment. If that's the case, then we will have textural effects also, adding a signal onto the velocity. So, we have multiple effects on our data, and out of that we are trying to tease out information about the fluid. So that's really the task that we set ourselves to investigate, and in these we define various properties. We look at pore compliance and mineral compliance, we look at models for fluid substitution, and we look at contact cements. Okay. So, what do the data look like? Well, we have velocity here as a function of pressure all the way up to 60 MPa, that's 600 bars. What units do you think in? Bars, MPa, PSI? Both? Okay, so MPa is fine, right? Okay. If I were in US, they would be very irritated with MPa, they would want it in PSI, but it's, sorry? You're working globally, so you know you have PSI and everything. Okay, right. Okay. That's good. So we are looking at velocity as a function of pressure. We have up to about 50 MPa here. We have two different types of rocks, a dolomite and a sandstone, very different. This is a calcium magnesium rock, carbonate rock. This is silica. The velocities, overall velocities are a little bit different, but the evolution of velocity as a function of pressure is about the same. So, I could describe an equation here and fit the same thing out here, and the development of velocity, the change in velocity as a function of pressure would be the same. Oh, because it is, so this is pressure going up, pressure coming down. It does look very similar. It is stress effect. So, what we are doing is we are compressing the rock and then we are releasing the stress. So, you have, we might have pictures for it, but you have different types of materials, things like this. So, if you apply stress to these guys, you can think of how much each one of them will change. This one will not change, this one will compress more, and this will compress maximum. In most cases, you go up, you have a certain curve, you come down, you have some curve that's similar but slightly different, because these things might not open again, you've closed them, whereas these just compress and come back. So, that's what you're describing as hysteresis. So, we have different rocks, same behavior. We can also have the same type of rocks. These are calcium carbonate rocks. Porosities for these are about the same, there is not much difference. But the velocity variation with pressure is very different here and very different here. In this case, we have primarily this type of pores. This is a fractured limestone. Out here, we have pores like this. They do not compress much. There is a slight change. I would ignore all this. Here and here, it's exactly the same. There is no change. These are two different directions of pressure. So, you have a rock like this, and we have aligned fractures. So, I am measuring this direction and I am measuring in that direction. This direction measurement is here, that direction measurement is here, and I know this because this direction is changing a lot. So, we can see the effect of pore compliance. This is what we are going to exploit when we examine storage capacity. When we apply stress to a system, this compliance is what will allow us to fill in more carbon dioxide over and above the brine that is present. And we can relate these two different types of rocks. These are three different sandstones. A very stiff cement over here gives us very little compliance in the pores. Out here, a fair amount of compliance, and this one with a very weak cemented rock and a large compliance of materials. So we can convert all of this data into pore rock stiffness, frame stiffness, and mineral stiffness. So we typically say there is a mineral stiffness, there is a frame stiffness, and there is a pore fluid stiffness and a pore stiffness. This is the one which we are interested in. For the most part, we say this is very high. So if we are looking at compressibility, this is negligible. The frame stiffness is there. If we are not allowing fluids to move in and out, this can be ignored. And so we're really looking at frame and pore stiffnesses. So we can define the compressibility of a rock as the compressibility of the solid and the change in the pore volume as a function of stress. This is your porosity, this is your d phi. So this here is d phi by d stress. This parameter is this way of looking at rocks is very useful because our primary measurement is this one here. This we can calculate if we know what the rock contains. And so with this one known and this one we measure as a function of stress. So porosity as a function of stress is known. So we can combine this here to get an idea of the pore compliance. And that makes it very interesting to use as a proxy for how much the rock will change when we add fluid to it and we change the stresses. This here is in the dry state. We also can write this equation to get the dry state, K dry, to K brine and to K brine plus CO2. So these are some of the models that we use to assess what's going on. Okay, so we were looking at pore compressibility and we defined a few terms and we said we can define pore compressibility in a manner like this. We can also look at, we can do these sort of assessments where we take porosity, and these are just models of pore compressibility as related to normalized by the pore or by the mineral. And so this is the same, this is the mineral, right? All the way down to porosity of 1. Normally we would tie it into critical porosity, but let's not go there. So we can plot our data in this sort of a plot, in this sort of a template, and try and get pore compressibility for each material so that we can use that. We can use the curve to say how much capacity we might have. So that's one way of doing this. We can also go in and look at change in velocity over initial velocity. This information is coming in from lab data at no pressure. This is where we are at benchtop, And then as we start increasing pressure, we start getting these. There are some that have really very high change in velocity. There's about 30% change in velocity over the initial velocity. In this case, only about 5% change. And so we see that depending on what sort of material we have cracks over here, and we have very stiff pores in this case. So we see a difference in change in velocity as a function of stress. Okay, so where does that take us? If we are looking at seismic information, where does that take us? Well, very simply, this is density, velocity, shear velocity, compressional velocity. No, this is not compressional velocity. This is, I do not know what this is. There cannot be a velocity of 14 kilometers per second. This is shear velocity, that is clear. I'll take a rain check on what this is. I have no idea. It could be anything. But the part which we are looking at is not. Sorry?
The previous chart.
Uh huh.
You are showing with the video.
This one? This one? Yeah.
Yeah.
Right. But the values, I'm looking at the values. This is 4.5 kilometers per second, right? And when we go to this one here, this is 4.5 kilometers per second. This is 14 kilometers per second. It's not possible. So I have some error in here. I do not know what it is. I'll find out, and as soon as I know, you will know. But this is the type of information we use, and we create models, right? We create mixing laws, and that's what I was talking about when we said we have a challenge, because we have at the simplest, we have a rock framework, mineral, and we have fluid. And so we want to combine those two. The easiest way to do that is what is known as the Royce and Voigt model. This is the stiffest way to build a rock. Here, all of the solids are load bearing and the fluids are inside, not bearing any of the load. And so, if that happens, then we get a very stiff matrix. If we have both the rock and the fluid load bearing, then the weakest material will define the overall stiffness. In this case, the stiffest material will define the overall stiffness. So, when we mix them, these are two extreme ways of mixing. This is the stiffest way to mix a rock. This is the weakest way to mix a rock. And in that, there are data. There are data from many different places, and you see none of the rocks occupy the stiff part. Most of them lie in this range here. These here are suspensions. So, suspensions lie almost on the fluid line. This is mixed with brine, so water, and so 1500 meters per second is your velocity of brine. So, these are suspensions here, and at some point you see that they lift off from this low curve from the Royce model, and the point where they start lifting off is what we call as critical porosity. It marks a threshold. This is almost, it's like a percolation threshold. You have fluid supported systems here. You get rid of most of the fluid, you start getting a rock framework supported system, and you start increasing velocities. So, that's the way we look at information. We can make this a little bit more complex, where we can, before we go there, we can take the velocity here and we can calculate. This is our porosity, we can calculate what the velocity should be. If we have seismic data, we were looking at well logs, we were looking at seismic data, what we are getting is velocity information. If we have that information, we can go in and say what the say what the porosity is. But here we have a challenge because there is ambiguity. It could be 18% or it could be 35%, right. So, that really is the part that we spend all of our thought process, not all, but most of our thought process on. What is this mixing law? What should it look like? We can calculate bounds. This is the two bounds. We can do the calculation. We can also have a little bit more complex bounds. And we can say this is a very typical from material science, the Hashing-Strickman bounds, where we have a stiff core with a soft outer material or a soft inner core and stiff outer material. That gives us a Hashing-Strickman upper and a lower bound. And so that allows us to constrain the data more. So if you remember, this is what we were looking at. These are the same data, the grain supported and a fluid supported medium. And if we then go further in that, this is what the data look like once you've cleaned it up and you've had more data input. And these are many different types of data. This is data from Deguo Han, this is from Troll data in the North Sea, and these are a lot of my own data. And so we can have the lower Hashing-Strickman bound, and we can put in models that allow us to now start to explain what the velocity looks like. All of this is done in the effort to say, if I have a velocity here, what should the porosity be? That's the part that keeps us up at night. We can also do something else. We can make measurements in the lab. These are measurements made in my lab. We have velocities as a function of porosity. These are many different rocks, a shear velocity, compressional velocity, and we get some sort of a correlation here. If you ignore these 2 points, then you get a correlation, a goodness of fit of about 0.91, 0.92, which is pretty decent. Now, we can take all of that and we can convert that. This is seismic data. This is data on cores, data on the scale of couple of centimeters derived from one location on this field here. So, you get a core from somewhere here, you measure that, you get cores from many different locations here, and you develop this sort of a relationship. Once you have that, now what you're doing is you're taking this seismic map and you're converting this impedance map into a porosity using a correlation like this. We have an impedance correlation with porosity, and so we can take this relationship and invert this into a porosity map. So now we have a porosity map that goes over tens of kilometers, goes down to depths of about 3,000 meters. And so that makes it a very powerful tool to use to have a description on what porosity variations look like. This is collected in 3 dimensions, x, y, and z. And so if we have a map on how to invert for porosity, we can get a seismic porosity cube. That seismic porosity cube then allows us to develop reservoir simulation models where we are doing flow from one side, production on the other, or pressure gradient on one side, equilibrating out into the reservoir. That tells us how far the fluid will go and where will it reside. In all of that, we are using trends and we are using understanding like this. These are porosity velocity logs from ocean drilling program data. This is depth, meters below seafloor, porosity, compressional velocity.
One
Yes, so this is velocity, this is correct data, this is numbers are correct. So this is 1500 meters per second, that's seawater about, and then as you go deeper there is a compaction trend, you can see it over here, your porosity is reducing, it's around almost 75% porosity. This is suspension, it's mostly suspension, it's mud. And as you're going down, you're going further and further down, your porosity is decreasing all the way down to about 35% at a depth of 500 meters. Corresponding to that, you have a change in velocity. We can put trends to this, that is the trend for A to B, and that's based on data. Now we can build models with it. We can say we have an early cementation model that's out here. As soon as you have cementation, your velocity jumps up and increases. Your porosity does not change that much because now you have a stiff matrix. On the other hand, if you add pore filling material, you don't get much of a change in velocity, but your porosity reduces quite a bit. Together with that, you can get permeability plots. So these are velocity permeability plots. These are different hydraulic units. These have similar flow properties. And so what we can do is we can go in and say my initial pore geometry corresponds to this cyan color. And if I do nothing else but change the pressure, the stress, go down in depth, I will just keep going down on this curve. Velocity will increase, permeability will decrease. But if I add a pore filling material like this, I can get a change in my hydraulic properties. I've added a pore filling material, and so now I've gone from this zone to this zone which has a different pore geometry. And so now my data would go along this line. If I add a pore stiffening material, if I add a cementation, then I would have a transportation from or a transfer from this line over to another line with a better hydraulic unit. And so my data would go along the green line. So we can play what if scenarios like this to determine what mobility the fluid would have based on permeability changes that are mapped to seismic data. So that's really the power of using seismic and getting core calibrations, because it allows us to map in the subsurface where the fluid might be going, what the fluid properties might be. Okay. Since we are talking about compressibility, let's take 5 more slides and then we'll stop. I can see that there is a little bit of fatigue happening here. I know you're all awake, you're all paying attention, this is fantastic. I love to hear myself talk, but I don't think we should do that too much. So these are idealized pore structures. This is what, and this is a fracture here, there is microporosity in here, there is dissolution features, there is intergranular, there is intragranular porosity. Geologists love to put names onto all these things, and I think they do that just to confuse the rest of us. But we see a change. So if we have round pores, if we only have pores like this here, only pores like this is what our velocity change will look like. Right? There's a benign change, you can describe it with either an exponential or some change. As you start changing the shape of these pores, we start seeing a difference. The end might be exactly the same, but this one here with ellipsoidal pores gets to a high velocity faster. If I have cracks, it doesn't take very much stress to reach that end velocity. And so we in mineral physics, we look at this part as saying this is really, this porosity is part of the rock. This is the part of which is compliant. The rest of it behaves like a mineral. So we can describe the behavior of a rock based on this K naught or velocity V naught and a pressure dependent curve. And that's pretty much what we do when we look at rocks like this. Is exactly, if you look at this one here, this is the rock that is deforming a lot, and here is a rock that has ellipsoidal pores. And this one here is at V naught or K naught. It is not at mineral velocity. Quartz velocity is much higher. If it were pure quartz, we would be at 6 kilometers per second or 5 kilometers per second, depending on the type of minerals there are. We are here at around 4 kilometers per second, which means that it is stiff, but it is not a mineral, which means there are pores that are part of the mineral framework. The reason we want to look at this is because of the relationship between pore geometry and texture. We have, these are a little bit different type of data. These are nuclear magnetic resonance data. Is that a concept, NMR? So, this is low field, this is not high field. This is low field NMR, so we are looking at the dipole. So, it is hydrogen, but we are looking at magnetizing the dipole and then letting it relax, and magnetizing, letting it relax. So, that is really what we are looking at. This is not a compositional NMR. This is just the hydrogen relaxation NMR at, I think this is about 2 Tesla. So, not 2 Tesla. So, very low. This is so what we do here, we use the NMR not for how chemists use it for analyzing the structure, but we use it for analyzing pore structure, because everything that is in the material is all hydrogen. That's the part that is acting as a magnet. So when you apply a magnetic field, all of the hydrogen in the pore fluid align. And then we look at the relaxation of when it goes back to disordered state. And we keep doing that till we get a relaxation spectrum. We take that spectrum and we then analyze or invert it into a pore spectrum. This is here T2 distributions. This is the T2 relaxation spectrum. And that defines really what the pore geometry is. So we use it really. If you have free fluids, that would come in somewhere here. If you have large pores that are here, smaller pores out here. We have 2 different structures. This is the schematic sketch of what we have. Again, none of us are artists, so these are 2 PhD students. They have since graduated and gone on to bigger and better lives. But when they were doing this, we were playing around to say, how does texture change anything? If you have laminated clays, we get a bimodal distribution, and the first peak here is imaging these guys. The second one is imaging the clays, and the different parts here are defining how much clay we have. The sand is pretty much a single distribution here. So that's really the sand. And we are adding layers of clay, more and more layers of clay. All that changes is the second peak, because that's the contribution of the clay. If we mix it, this is the sand, and we mix it, now all of the pore spectrum shifts. We start getting large pores, but in that large pores, they are compromised by the presence of clay. And so when we examine pore structure, this would be one hydraulic unit, and this would be a very different hydraulic unit. Right? So when we are looking at compressibility, becomes really interesting, because this would have a very different compressibility. We have depending on whether the stress is unidirectional in this direction or in this direction. If it's in this direction, then this part would be affected a lot because that's the weakest part. If it's in this direction, then we would change these pore fluids, pore types. And so pore stiffness and pore compliance becomes tied in to pore distributions. So I think all of that ties into what we do as a map. These are seismic amplitude maps. What they're describing is high amplitudes, these yellows that come out very well defined over here and start distributing on this side. What we're looking at is the seismic expression of a submarine fan. These are slump structures. When sediment load becomes a lot, the sediment slumps and forms these avalanches in the seafloor. And this is a fossilized submarine fan. As you have that, you get a deposition of different types of materials. You have very high energy over here, and as you go away from the slump, energy drops. And so as the energy drops, you start seeing changes in your seismic properties. These are velocity data from well number 2, that's out here, and from well number 1, that's over here. And so the velocity structure is different if you are in a very clean, well sorted environment, because the energy of deposition was so large that all of the fine clay material gets washed away. And if that happens, you get data that lie along here. When you reach outside here, the energy of the water, the carrying fluid, drops, and you get a mix of materials. There is some clean and so on, and the velocity goes down, mainly because you have much more clay minerals in it. So when we look at interpreting data, we are assessing all of that information together. Okay? Okay. So let's stop here because we will reach a new place. Okay, geologic storage targets. Thank you very much.